So welcome everyone to the 2022 NOAA lecture series. As I was saying, this is a 5-part series with the overarching title of the role of turbulence in ocean, atmosphere, and science, and climate. So I was just going to highlight a specific achievement that Professor Ferrari has that he holds, which is the Cody Award. The Cody Award is bestowed by the Scripps Institute of Oceanography biannually for significant achievements in oceanography, ocean bioscience, and earth science. And Professor Ferrari received this award in 2016 for his work on understanding mechanisms for ocean mixing and its sometimes unexpected consequences. So today he will be presenting work of a field campaign for observing how ocean water rises from the abyss. And yeah, so let's thank Professor Ferrari for making it here during the challenging times we've had these last few years. And let's all give Professor Ferrari a big welcome.
Thank you. Now you can hear me right from this microphone. Oh, why this thing is. Is everybody happy to be recorded? Got it. Live streamed. Got it. Okay, so this second lecture builds on the one of yesterday. If you were not here yesterday, you should still be able to follow. But if you were here yesterday, probably a lot of, hopefully, some of the answers that came up will be addressed. And what we want to really discuss is to understand a bit how our understanding of the role of ocean mixing in the abyssal circulation has evolved over the last few years. And I should acknowledge this work is done again in collaboration with a number of former students, John Callis, Henry Drake, a collaborator from Australia, Trevor McDougall, that many of you might know of, at least because of the equation of state of seawater. He's a very strong proponent of details about that equation of state. Sophia Merrifield and Maxime Nicouragin were also former students a bit earlier than Jorn and Henri, and Kelly Ogden and Xiaozhou Ruan instead are postdocs that are still working with us. So again, to put the work in context, what we are trying to understand is what is the dynamics that drives this strong overturning circulation. This, of course, is a very limited schematic that tries to just portray the fact that we have warm waters that move at shallower depths in the ocean, and then they sink at high latitudes because of very strong buoyancy loss. They sink in the abyss, and then the big question is how they come back to the surface, because they cannot be warmed directly by electromagnetic radiation that doesn't penetrate that deep into the ocean. And we seen yesterday that indeed we think that turbulent processes might have something to do with it. Again, the beginning of the talk should be just a summary of what we've seen yesterday, just to frame what the question is, because in this particular problem, the question is probably even more important than the answer, asking exactly what part of the problem is difficult to understand. Again, this is a simple schematic of the supposedly deep ocean circulation. So we have depth on the vertical axis and latitude on the horizontal axis, going from the southern hemisphere to the northern hemisphere with the equator in the middle. And as we see, and then maybe I should say the blue shaded area is representing bottom topography in the ocean, the deepest bottom topography. And instead, the red line is the typical height of mid-Atlantic or Pacific or Indian ridges or sea mounts that tend to stick up all the way to close to 2,000 meters in the global ocean. And if you want to know why it's 2,000 meters, the geologists around on campus can answer that question. But there are very good reasons why it really reaches up to that level. It depends on the weight of the crust that is formed. So the first question that we said is that that structure is associated with the density stratification, meaning that the ocean is getting denser as we move deeper down. Actually, just as an anecdote, it turns out it was the chemist Boyle that first realized or pointed out that probably the ocean is coldest or densest at the bottom and lightest at the top. Until then, the common assumption was that since there is geothermal heating coming from the bottom of the ocean, probably the ocean at the bottom was lightest. But by then, people started realizing that is an unstable configuration. If you have light water below dense water, very quickly it overturns. That's what we see in the tropics in the atmosphere all the time. But now we know that that is stably stratified, so we have to understand that whatever theory we have, it has to account for the change of density with depth. We've seen that water sinks at depth only at high latitudes around Antarctica to the left. And, or maybe I should use the mouse, otherwise anybody who's not in the room doesn't know where I'm pointing. Sinks at depth around Antarctica in the south and in the North Atlantic, primarily in the north. So there are these two regions where water sinks into the bottom for a combination of reasons. As we said, there is very strong buoyancy loss, but it's also that the ocean is particularly weakly stratified, meaning density doesn't change with depth as much at high latitude as at low latitudes, and therefore little cooling can effectively make waters as dense as the water at the bottom. We've seen that there are two circulations in the abyssal ocean. The first one that I depict here is a circulation with water that sinks in the North Atlantic, flow mostly at the depth of above the depth of typical ridges and seamount, all the way to the Southern Ocean, where it's brought to the surface by the divergence created at the surface by winds blowing over Antarctica. So the water is really sucked toward the surface and then comes back in a loop that sits above 2,000 meters, mostly in the North Atlantic, well, North and South Atlantic. Instead, we also have a second circulation, which is what we're focusing on now, where water sinks around Antarctica, flood into the abyssal ocean, and then they seem to be able to come back to the surface as lighter water. So they've really changed their density. They must have crossed density surfaces in this pathway. And we reviewed that potentially turbulence might have something to do with it, which we know a bit a priori. Well, we didn't know a priori. We knew that it couldn't happen with direct electromagnetic radiation from the sun because that's all absorbed very quickly close to the surface of the ocean. It could have been molecular processes. There is always some mixing. I have warm water over cold water. Eventually, some of the warmth is mixed with the bottom of that. Walter Mank showed us yesterday, well, or she showed us in '66, but we reviewed yesterday, that process is incredibly slow and couldn't account for the strength of the circulation and stratification we observe. So what we want to understand today, now I'm just putting a picture, which is more the picture of from a real estimate from the global ocean that we've also looked at yesterday. This is depth and latitude. And we are trying to understand why is it that there are 25 Sverdrups of water that sinks around Antarctica, comes to the bottom of the ocean and return back to the surface. Sverdrups is, one Sverdrup is 10 to the 6 meter cubed per second. So this must be something close to, but now I have to be careful. I think that, for example, the Amazon River is transporting something of the order of 0.2 Sverdrups. So this is 50 times the transport of the Amazon River. It's an immense amount of water that goes around to the ocean. That loop takes a long time to complete. We know that it takes an order of 1,000 years to complete. And so we want to understand a bit what sets these water masses in motions, because as we also discussed yesterday, they have important implications for the interaction between the ocean and atmosphere, at least on long time scale, because a lot of the progress like heat and carbon and enter into the ocean are affected along that loop. So we are going quickly, but I'm just reviewing what we said yesterday, and now we're going to get into the dynamics. Oh, here this, why is that thing at the bottom? Can we erase this thing? We lost the technician. Because I don't think I can do anything from this side. I don't have it on my screen, so it's from whoever is handling the Zoom. Can we just erase or eliminate this bottom bar? Well, I keep talking while you try to eliminate it. Should be able to move it at least towards the top. Close.
Maybe it'll go away.
Good guess, but any other? Well, okay, we can live with that. If you can figure out in the meanwhile how to take it away. Oh, wonderful. Thank you. Now hold your breath. Yeah, I see. Oh. So this was reviewing the concept that we brought up yesterday that suggested that this is work that really was done by Henry Stommel, or Hank Stommel, as he was known, and Walter Munk. That suggested if you have all this water sinking at high latitude, these 25 fathoms of water, said, well, it has to rise somewhere. They assumed it was rising uniformly to the rest of the ocean, and they got therefore an upwelling of 3 meters per year. And now they said what really Walter Munk suggests is that there is all this water sinking from the abyss toward the surface slowly. It's rising very slowly. We said it's very slowly, but it's a lot of water is coming out. So he was asking, well, this water is moving towards the surface. It's getting lighter. It has to be getting lighter because it's coming toward the surface where water is lighter. So you have to diffuse heat downward to warm this water constantly. And so Walter Munk just decided to just try to write this simple budget where you have advection of buoyancy from the bottom of the ocean toward the surface. So W is your vertical advection, and dBdz is your stratification. Is balanced by diffusion of heat downward. This is just the diffusion equation part. It's just the Fickian law, and said, well, let me assume that the turbulent, or the diffusivity that is diffusing heat, so the rate at which heat is diffused, is constant as well. He had to assume that. He had no measurement at the time of what that could be. So he just assumed, well, let's see what number we get out of it. And this simple equation now has a single derivative in z and a double derivative in z and a coefficient that is positive. So because both W naught and kappa T are positive, so the ratio of the two is positive. And this equation then has exponential solution. And Walter Munk wrote this simple exponential solution that has what is called the Niffolding scale kappa T over W naught, meaning that the rate at which the stratification is changing with depth is set by the ratio of these two parameters, kappa T and W naught. He knew W naught, so now he went to data, he fitted an exponential curve to the profile of temperature in the Pacific. Walter Munk was at Scripps, and therefore the Pacific was easier for him to access. By the way, interestingly enough, most of the work that Henry Stommel did to estimate the W naught instead was in the Atlantic, because Hank Stommel was at Woods Hole, so easier for him to be measuring in the Atlantic. So all these estimates generally take a mixture of whatever ocean was in front of your window. And so if they fit, or Walter Munk really fits an exponential to this profile from the Pacific, and finds out that Niffolding scale, or the rate at which the density changes with depth, is about 830 meters, meaning that this buoyancy, this temperature, in this case is decaying by a factor of E 2.7 over 830 meters. That's what you see here. Given that he knew W naught, he estimated what was kappa T, and that told him that there had to be a pretty large, or 10 to the minus 4 meters squared per second, 3 orders of magnitude larger than molecular diffusivity process in action that keep diffusing heat downward. Essentially what we said yesterday, like spoons that constantly mix, and these spoons are supposedly breaking waves. So we're nearly done with the review of yesterday. The physical oceanography community got excited at that point because you're really looking for this strong turbulence supposedly very deep into the ocean, except that when we say very strong, you're talking about velocity of order of centimeter per second that just generates small fluctuation of velocity in the deep ocean, and you want to measure it a few thousand meters below the surface. And you know that you're sitting on a ship that is blowing over surface waves that are moving much faster than that velocity. So it's not that easy. In the end, the solution was to use this vertical resolution profiler developed in Woods Hole. Now there are other versions. What that does is that it's an autonomous vehicle that sinks into the ocean at a pretty much constant speed. And it has a small piezoelectric element at the top. Piezoelectric element is such that if you deflect it, it drives potential or a current that you can measure. And why is it important? Well, because when it's deflected, this piezoelectric material sticks in the water in front of the probe. So every time there is a current, that suppose it's associated with a breaking wave that generates some velocity in the horizontal that keeps changing, this piezoelectric element moves back and forth, and that is recorded. And so you can see the level of turbulence as the profiler is falling through the water column. When they did this kind of experiments, what they found is what we suggested yesterday, that the turbulent mixing or the rate of mixing of buoyancy, this term kappa TdBdz, this is what they were measuring, was increasing towards the ocean bottom. And if that's the case, then the ddz of this term is actually negative, because I take z is increasing upward, and indeed the buoyancy profile, the buoyancy flux is decreasing as I move upward, which seems to invalidate the argument of Walter Munk and Henry Stommel, because now it's suggesting that turbulence is strong, and it's actually observed. The value of kappa T itself, we see it here now. Well, it's not plotted here, but the ocean bottom gets to value even in excess of Munk's estimate of close to 10 to the minus 3 meters squared per second instead of 10 to the minus 4. The number is not the important thing, but it was 10 times larger than even Walter Munk suggested. But the fact that it's increasing towards the bottom, in terms of that budget, is suggesting that the velocity should be sinking instead of rising. And so now you have a problem. You thought you solved one, but you created a new one, which is probably not unusual in science. You answer a question, but now you have a new one coming up at you. But we said that we probably can understand the inconsistency again, because through water is sinking, and again, the reason why it's sinking, now we understand. We discussed yesterday the turbulence is mostly generated by waves that are formed when paratropic tidal geostrophic motion rub against rough topography of the ocean bottom. So you generate the waves and they break close to the ocean bottom. So mixing is much more intense close to the ocean bottom than farther aloft, because some waves manage to penetrate farther up, but most of them break close to the seafloor. Much like surface gravity waves tend to break close to the shore and not farther offshore. Some will break before, but most of the mixing is confined close to the topography also in that case. So if you have a water parcel in the middle of the water column, it's mixed more with water below than with water above. And the water below is denser. So if you're mixing more with water below, that water parcel is getting denser as a result of mixing and the mixing profile instead of getting lighter. And so it sinks. But we said that it sinks all the way until it gets to the ocean bottom. When it is sitting on the ocean bottom now, it's been mixed only with lighter water above it. So water particles sitting on the bottom now, finally, it's experiencing only warming in a sense, because it's mixed of warming, or made lighter because it's mixed with warm water above it. That allows it. So if it's getting lighter now, it starts rising along topography, but it really has to rise along a topographic feature. So now we want to understand how. Hopefully this is the end of the review part. We reset the problem we were at. Now we want to understand a bit more in depth, both what is the dynamics that drives that circulation under the understanding of the buoyancy budget that we discussed until now. And then we'll see how, a bit more in detail, how we use an experiment to test the ideas that I'm going to describe. So what we're going to use to describe the dynamics of this large-scale motion are just Newton's equation, essentially, for a continuous fluid, or they're known as the Navier-Stokes equations, under a few approximations. The first one, you see, the first equation is supposedly the horizontal and vertical momentum equations, except that on the left-hand side, I don't have the full acceleration. I just have the Coriolis acceleration, because relative acceleration are supposed to be small. What it means that these motions are evolving very slowly on time scales lower than the rotation of the Earth. And as a result, the circulation is pretty slow, and it feels mostly the Coriolis acceleration a leading order. So we can drop, if there are dynamics in the room, the du dt term that would appear. Essentially, the only acceleration you care about when you drive. But if you were a very slow driver that drives on timescales lower than the rotation of the planet, then you would worry about the Coriolis acceleration. On the right-hand side, the forces that are acting are going to be pressure gradient forces that act on a fluid. Buoyancy, this is just the fact that density is changing with depth. So it sets forces because there are water of different density on top of each other or laterally. And then this equation is only describing large-scale motions. And if you take in any class in fluid dynamics, when you try to describe only large-scale motions, there are always the effect of smaller-scale motion that you're trying somewhat to account for, because you're not resolving them, but they can have an effect on the larger scale. So essentially all the turbulence that you're trying to sweep under the rug, but it still has an effect on the mean. And in particular here, I'm using a linear drag to represent essentially the turbulent flux of the small-scale turbulence on the buoyancy field. The results don't really depend on that form. You could use forms that people might prefer, like a divergence of a momentum flux, you can do that. The solution really doesn't depend sensitively on those choices, at least in a qualitative sense. So we are using the simplest form that we can think. So what I mean, a Rayleigh drag is just some constant times the velocity. So that turbulence is just slowing the momentum or the velocity field in the fluid. We are also, the second equation is conservation of mass. In this case, since the ocean is nearly incompressible, water does change density a tiny bit as you warm and cool it, but not by much. So we can just assume that it's essentially a conservation of volume, or a conservation of volume, meaning the velocity have to be divergence-less, because you cannot converge fluid in a smaller volume at any point. Volume have to be conserved. And the last equation is the only equation that has nonlinear terms. Nonlinear terms means when you have products of two terms in the equations. And the buoyancy equation, therefore, it's the advectional buoyancy, U dot grab B, the fact that the velocity is moving buoyancy, or if you don't like buoyancy, we said yesterday, buoyancy is minus density anomaly, if you want, multiplied by G. So it has units of an acceleration. But if you don't like buoyancy or it confuses you, just think about potential temperature or temperature. So U dot grab B means that temperature is advected around, because as the fluid moves, it will move heat with it. And it's being diffused. That's what Walter Munk told us. Again, since we are describing the motion on large scale, then we have to represent the effect of the small scale turbulence. And as Walter Munk suggested, we assume that the turbulence is just mixing the fluid. And so we just use a Fickian law. Again, what we're going to be particularly interested in these two aspects in this problem when we solve this equation. These are called the planetary geostrophic equation. They are solved in many contexts. Here, the two aspects that we want to put in the solution of this equation are the fact that kappa T, this turbulence, is increasing towards the ocean bottom, because that's what the evidence of observational evidence suggests, at least when you're over rough topography, like over ridges and seamounts, where kappa T is substantial. And the second thing is that the topography is not going to be flat. Indeed, those are both elements that had been ignored in previous literature, starting from Munk and Sommer, and we'll see that both of them play a very important role. So you have to account that. Like, every theory should be as simple as possible, but not simpler. And we would contend that was Einstein, right? And the last 2 points is, well, something that probably if you ignore, you're making the theory a bit too simple to account for the real dynamics of the system. So let me first see, we can actually solve those equations numerically if we want. And we're going to use a pretty simple setup. This is the topography we're going to use. We are trying to represent something that might look a bit like an ocean basin. And so there is a box that is our rectangular ocean basin. You see the topography is getting shallower on the edges because there are continental shelves. The ocean gets shallower in the edges, but we also have a ridge in the middle because we said mixing is mostly confined to ridges and seamounts. To the south, all ocean basins are connected. We've seen it yesterday. All ocean basins are connected to the south, to the Southern Ocean, which instead is a big zonal reentrant current that goes all around the globe, which is pretty different. So we're going to have to mimic what happens in that Southern Ocean system where the flow is actually zonal and reentrant. Here, just to keep the problem simple, instead of having to solve the whole dynamics of the Southern Ocean, which you could put in this system, but instead we just say, well, what happens in the Southern Ocean, we are going to restore our buoyancy profile to some mean profile that we prescribe. All that happens in that part of the ocean, since there is this restoring, you generate new dense water. Every time the water gets to the Southern Ocean at the surface, it's transforming denser water, which is to leading order what happens. And this is a simple way to achieve that, but keeping under control, because our question is more how water comes back to the surface, which is what happens in the ocean basin, not as much how water sinks into the deep. And so we want to keep, again, the problem simple enough that we control the part of the solution that we are interested in. So our equation for buoyancy has this additional term, which is a restoring of B to some capital function B, which is a function of depth only, but that acts only in the effective Southern Ocean domain, right? Now, what do we do? Well, our problem will start with some boundary condition. We're going to have no heat flux through the solid boundaries because there is no heat. There is some geothermal heat. We can comment at the end what the effect of geothermal heat would be. It actually reinforces the solution we described, but for the moment, let's assume there is absolutely no heat. The geothermal heat is a small heat flux anyhow. There is no normal flow through the boundary. Both of those had to keep into account that, well, there is no flux through the surface, that's fine, but on the side instead, the topography is not flat. So when we say no heat flux is normal to the boundary. And in terms of mixing, now this is a section of taken at close to the equator, I guess, in our basin domain. And so now you see our ocean basin. These are the continental shelf in this simple model. And this is our ridge. And you see the mixing. The color is how strong is the mixing, and mixing is largest right above the ridge. Only about the ridge and not as much of the continental shelf. The reason being that, as we described yesterday, region and seamount are new crusts, so they're very irregular and uneven. They are very effective at generating internal waves that are pretty small scale waves that you need the small scale corrugation to generate waves of the right frequency that can propagate into the ocean. Instead, the continental shelves are much older topographic feature. They are much smoother. They don't generate internal waves as effectively. And so we're trying to mimic that. So we now see that the two elements are there. Mixing is confined just above topography. So it's largest at the bottom, it decreases with height, and the topography is clearly not flat. So if we just take this model and you run it all the way to equilibrium just to understand what happens, you see the picture on the left that again depicts the overturning circulation in this model. You should think about this model as just a model of the deeper overturning circulation. That's why if you look on the vertical axis, we are only considering depths, say below 2,000 meters or so, or 2,500 meters or so. So we're just looking at the abyssal portion of the circulation. So let's say that we are in the deep Pacific. Again, the gray line is our bottom topography, but the red line instead is showing the height of the ridge that gets pretty high up in the water column. The model, I think, is run on a much deeper domain, except that we're not showing what happens on the top because not much happens there. So again, as I said, in the channel portion of the domain, which is pretty much south of where the Mid-Atlantic ridge disappears, the effective ridge disappears, not Mid-Atlantic, just an idealized ridge. So south of here, there is this restoring terms that makes water sick, and that's all it has to achieve. Now, the interesting part of the solution is what happens elsewhere. So it seems that if we look at this overturning stream function, these stream lines, where we see the water is coming into the basin at depth and somehow is crossing density surfaces and returning back. At the surface, most of the circulation is really confined below the ridge. It's not above the ridge. Above the ridge, the velocity drops quite rapidly. The strength of the circulation, well, in non-dimensional units is whatever it needs to be. It's not very different from what you would get for an overturning circulation of a global ocean, as long as you use realistic parameters for the diffusivity and the profile I restore north here. In any case, qualitatively, you see that the circulation has this counterclockwise sense, much like we've seen in the picture of the real ocean. So qualitatively, we are getting the same kind of overturning circulation. Now we want to understand where it comes from. I'm showing it here. So this blue is a bit the same as the blue here, at least in terms of the sign of the circulation. Now we can look a bit more in detail about what the solution is actually doing. If I take a section, again, pretty close to north of the equator, again, this is our topography, and now it's longitude section, east-west. I take a slice of the ocean and I plot here the velocity field, just to see what happens. And if I look at the velocity field, well, red means positive upward velocity and blue downward velocity. And you see that we start having this pattern that we described yesterday. It seems to be very strong upwelling along topography, but there is some sinking just above it. So there is a dipole pattern of water rising along the topography and sinking, and that is mostly confined to the region where there is strong mixing. There is still some upwelling along the continental shelves, but the magnitude is definitely weaker than it is along the ridge itself. And so already what we can say is that when I look at my overturning picture, it's true that there is upwelling of, let's say, our 25 square groups of water, but that is the result of two motions going in opposite direction. A lot of upwelling along the boundary, this very strong and thin red, and downwelling happening right above it, which is weaker, but is spread over a larger distance. So the two largely cancel, or at least this 25 square group is supposedly a small residual of larger terms. this seems to suggest, okay, that what is happening along the boundary is what drives the conversion of water from dense to light, because fair enough, some of the water gets denser until it gets to topography, but then it goes on a very high-speed highway along this thin boundary layer, comes all the way to the surface. So that's where the water mass transformation is happening. But you might ask, well, but water still has to come from the Southern Ocean to the north and come from the higher latitudes back to the Southern Ocean. So where is the meridional transport? Because so far we only talked about the vertical transport. Well, if I look at the meridional transport, I will show now a section here again. This is now showing the meridional velocity, right? So far I was looking at the vertical velocity, now I'm looking at the north-south velocity components. And if you've taken any classes in physical oceanography, you know about the concept of western boundary current and the fact that in a rotating planet, you tend to have very strong currents abutting western boundaries of the basin. That has to do with the fact that, well, I don't know if this helps or not, but in the ocean we have, in geophysical fluid dynamical system, because of the curvature of the Earth is rotating, but it's also curved. You get what are called Rossby waves. This is a form of waves that tend to propagate always westward. So you always transport information in ocean basin from left to right or towards the west. And that accumulates information in this transport on the western side of basins. So what we see here is that if I look at depth, I have two western boundary currents abutting, well, the ridge and the shelf here. You can have two of them because both of these are on the western side of whatever is the right basin and the smallest basin. In a sense, they are separate by the presence of that ridge. So this is water that is moving northward towards higher latitudes. So this is this red line that is taking water from low latitudes to high latitudes along the bottom topography. And then instead, if I look at the top of this picture, I have a strong current, western boundary current coming towards me. And then the water comes back towards me. So it's this western boundary current that do most of the meridional transport. And if you look carefully here, I'm not sure, it's virtually impossible to see, but these western boundary currents are associated with deflection of density surfaces, again, east-west. This is an effect, again, of the rotation of the planet. Every time you have density surface which is not perfectly horizontal, there are horizontal buoyancy gradients that are in thermal wind balance with zonal currents. So that's what is happening. So now we start having a full picture of, we know that there is upwelling happening along the boundaries and north-south flow along western boundary current. Now I want to spend a bit of time in understanding a bit better this upwelling along the boundary, and then the next step will be to connect this flow that seems to be moving or transforming water along a ridge, but then the north-south flow, right? The problem. Now, the question that we might have is that we have flow moving north here and moving back as cold water there, but all the water mass transformation is happening along the ridge. So we still have to communicate that information across the whole ocean basin in the east-west direction, because the flow is coming to the north, but all on the western margin, and all the transformation is happening on the eastern margin of that basin. So let's look a second at the, what we call a boundary layer solution, meaning the solution along this sloping boundary, which I guess is what Paul was asking about yesterday. And the best way to, so we want to see what is the stratification and the dynamics of the flow under these two conditions, that there is a sloping boundary and that the diffusivity will increase towards the bottom. But for the moment, let's do an even simpler problem, which is we assume that the diffusivity is constant. It will turn out even with constant diffusivity, you get some of the effect we described, having a depth enhanced, the Pigna diffusivity will actually enhance that effect. But so for the moment, let's look at blue lines, which means the solution for constant turbulent diffusivity. And we are in this reference, well, we are in this tilted system. It turns out that it's actually easier to solve this problem if we rotate our reference system with the topography. So instead of working in the up-down and east-west direction, we tilt the system to move in the direction normal to the topography and along the topography. And it will be clear in a second why that is actually useful. Or maybe I can already say it here, is that big part of the problem, or why it's a bit more natural to work in that direction, is that we know that the flux normal to the boundary has to go to zero. The buoyancy flux across this boundary, this is my boundary here, is the flux in this direction has to go to zero, which is in the direction normal to the boundary, and I like that to be my vertical coordinate. So we are introducing this new coordinate system that has, which I call x prime and z prime, where x prime is the direction along the boundary and z prime is the direction normal to the boundary, while x and z were purely horizontal and z is purely vertical, right? So, and I also am going to assume that there is some background stratification in the interior of the flow. For the moment, we just prescribe that. So we have our total stratification is some background stratification. Our total buoyancy is some n squared z. So this is the density that increases with height in the interior of the ocean, plus small b. It's a perturbation which we want to see what happens when we get close to the boundary, because that stratification has to be modified as we get close to the boundary. And if I rotate my reference system, then my n squared z has a component along the topography and a component across the topography. And that is very important. I mean, you can think, I mean, there is nothing particular subtle. Well, now I'm going to break all rules probably. But I have, this is my topography and this is my stratification. So now if this is what I call the n squared z stratification, the fact that density is changing in the vertical with depth. And now you see, if I look in the x prime coordinate reference frame in this direction, there is a stratification along the boundary in that direction because the stratification is intersecting the boundary. I'm back. So what happens when you try to solve this problem? Well, the first thing you can think of is that we insisted we have a no-normal flux boundary condition at the boundary, right? No heat can cross the boundary, and that boundary condition means that kappa t, the turbulent diffusivity, times the vertical gradient normal to the boundary has to be zero, right? Kappa t, dB dz normal to the boundary, dB dz prime has to be zero. What that means is that your density surface, as the system adjusts, cannot remain straight. They have to bend and become normal to the boundary because I cannot have any gradient along normal to the boundary. That's the boundary condition, that no heat flux goes through that boundary. If there is any gradient along the boundary, since heat or turbulence is good at mixing across gradient, well, it will keep mixing into the boundary itself. So it's only by eliminating any gradient normal to the boundary that I stop the flux. So you see, now these density surfaces are bending into the boundary. This is the blue line for constant kappa for the moment. And that is consistent with what I said before. Think about this water parcel here. Well, this water parcel got, can you see my pointer? Yeah. This water parcel right here got warmer as a result of this mixing, right? Because the density surface bent downward. So now all of a sudden some warm water has moved in that direction. So that warming is taking on, or effectively what the warming does in terms of density surface, it means that all density surface has to bend down a bit because the whole boundary is getting a bit warmer than it was before because of that heat that is diffusing towards the boundary. So now you bend these density surfaces, and already at leading order you can ask a bit what is happening now along this boundary, because along the boundary I can write this budget for what is the across slope flow. Well, I now have the advection along the boundary, u. This is now velocity along the boundary, acting on my horizontal density gradient, which is what I've drawn there. There is a horizontal density gradient. So the velocity is transporting, or that velocity along the boundary can transport warm water, cold water upward, or warm water downward, depending whether u is positive or negative. But since if there is any flow along the boundary, it's going to start advecting water of different temperatures back and forth. And that has to be balanced by this divergence of the buoyancy flux, what I keep talking about, this ddz of kappa t bz, where now bz has these two terms because I'm in this rotated reference frame, but that's a bit irrelevant, right? So we know that heat flux, even for a force constant kappa t, if there is a flux that's coming towards the boundary where there is a flux that keeps coming down and coming down, it's constant if n squared and kappa are both constant. So ddz of that flux is exactly zero until I get to the boundary where all of a sudden the flux has to go to zero, and that's called a divergence. And so I have that this term all of a sudden they become large and positive. And so that must drive a velocity u upward to be in balance. Right? So I have all of a sudden a flow that is moving upward in response to this heat flux that is moving towards the boundary. And this is the budget. And it tells me that as long as there is a kappa T that is not exactly zero, there is a velocity responding to it. Not only that, but interestingly enough, well, let's stop here for a second. It just coming to the bottom. Now let's look at the problem if I allow kappa T now to be instead very small in the ocean interior and then increasing towards the topography. So I changed the problem a bit where now kappa T is not constant, but it has some structure. But if kappa T has some structure, all of a sudden we've seen that what must be happening is that now above the water column, because kappa T is increasing towards the bottom, I have a divergence of the heat flux. I'm actually cooling the water instead of warming it up. Because as I said, I'm taking heat away from the system in a sense. As I move downward, the heat flux is becoming larger and larger, so I'm really taking it out of the system. And then I accumulate all that heat right along the boundary. And so now we're looking at the stratification in the orange, and you see that the density surface therefore has to rise a bit above the about the constant stratification line because it's getting cooler. So all this water, the density surface moving up means that the water is getting a bit colder, right? Cold water is moving upward. So I'm warming, I'm cooling at a particular depth, but then they still have to bend to satisfy the non-normal flow boundary condition. So now you see what I meant by the dipole of cooling and warming. This water here, because the orange line is dipping into the boundary, is getting a bit warmer, but just upstream of it is getting a bit colder. These are actual solutions that go back to, I guess, Chris Garrett is the person who really pushed this kind of analytical solution. So now we see the cooling and the warming pattern. And again, we can solve this equation, this buoyancy budget, that shows us now that very close to the bottom where this divergence is positive, where heat is accumulated, then you must have an upward flow. While instead above, where you have cooling, the velocity has to be negative because this term is negative and therefore U has to be negative. But more importantly, one of the results that you see that starts being quite intriguing is that I could integrate in the vertical this equation, right? From the bottom upward, there is no heat flux at the bottom. If my kappa T becomes very small, high up above the topography, right? And I integrate in the vertical, both the bottom value and the top value are essentially zero. The bottom because the flux is zero, and at the top because kappa T is essentially zero. So it's telling me that the vertically integrated transport along the boundary has to be zero. What that means is that there is a lot of upslope flow close to the boundary, but that is all canceled by a return flow above it. So that's what we meant by the dipole. Why is it there a strong cancellation? Well, because in the net, if mixing is stopping some height above topography, well, you are only redistributing heat. You haven't generated any heat anywhere. So the upslope and the downslope flow have to exactly cancel. In this problem, you don't have only a flow along the boundary, but since now you tilt the density surfaces, if you have taken classes in geophysical fluid dynamics, what happens here is now you have a horizontal density gradient, right? The density here is different from the density there, right? Here I'm below the orange line and here I'm above the orange line. So there is a horizontal change in buoyancy. If you have a horizontal change in buoyancy, then you also have on a rotating planet, you also have a zone and a long, well, in and out of the page flow that is in thermal wind balance with that solution. So you also have flows east and well, north and south. You're thinking longer than I thought. Maybe we won't talk. Then I'll have to apologize to Paul. We could also get into the pressure forces and how those drive the solutions. But you can see the reason why this flow emerges is that I deflect the density surface and those drives pressure forces. Maybe you can just say it quickly, but you can see that you have light water next to dense water on this level. So that is applying a torque and it's driving a circulation. So if you want to think in terms of forces, that this torque is trying to push this water along the boundary upward and push the water above it downward. So now we understand a bit what is this boundary flow, why is it going upward and why we expect a return flow above and why the two should really nearly cancel. And they don't have to exactly cancel like in the solution we've shown before, because in the solution we've shown so far, we're assuming stratification is constant. If you allow the stratification to change a bit in the vertical, then some of the upslope and downslope flow don't cancel, but they generate flows that move east-west in what we'll see now. Now, what I'm going to show you from the simulation that we looked at before, there is a parcel here that is being released at that point, and we want to see its trajectory, because I said there is upslope flow. This is, again, a section depth and longitude. This is the upslope flow, and the blue line is the downslope flow. But I want to show you that the story is always a bit more delicate than you might think. You see this particle, every time close to the boundary, it moves up. As soon as it's outside of the boundary, moves down a bit, but it does exchange. There is a strong exchange of flow between the boundary and the interior. And so this parcel started really here. First, it went close to the boundary. It was sinking towards the boundary. Here is where all of a sudden it's advected up, but then it leaves the boundary, because the solution we described never talked about the flow exchange between the boundary and the interior. As long as it happens at a constant density, you're always free to move in that direction. Then the flow again ends up, the particle again ends up in a region of downwelling, so it comes to the bottom, but then it comes all the way up because it's really at the bottom of this boundary there, so it gets a big kick out pretty much to the top of the mid-Atlantic ridge. When it comes back here, finally, there is a weaker but still present upwelling along the mid-Atlantic ridge. That's where kappa T is constant, so the upwelling is weaker, but there is still some upwelling, and now this particle has made it all the way to the top. Why does it matter? Well, because this particle went probably from a region here, there was a western boundary current moving it northward, and it ended up all the way here where it starts being pushed southward. So we can actually look now from the top plane, longitude, latitude, at the same particle trajectory, and we see that for a while the particle is moving up, and then it will all of a sudden shoot back down. So now you've seen the water that was moving upward along this boundary, so water that was moving from the Southern Ocean to the interior, and then finally, when it's shallow enough, it finally taps into the western boundary current at the surface, and it can come back. So you see the exchange of water from the interior and the surface. And so the overall picture of the circulation that is emerging here is sketched here, where what we expect, so we are looking from the Southern Ocean toward the North Pacific. And what we expect is that there is dense water formed around Antarctica. This water flows along the western boundary current on the western boundary of the ocean, but then water continuously will flow towards the mid-Atlantic ridge. It just is spreading out because it can move laterally. There is no force impeding it from spreading out. The water that reaches the mid-Atlantic ridge is now experiencing this very strong mixing that allows it to slide above this rough topography, and so it moves actually up the slope. But some of it will move down the slope right above it, because we said that there are slight differences. So there is both an upslope and a downslope flow. But this water exchange with the interior, this is something I didn't discuss at all. This exchange between the boundary and the interior is forced to occur if your stratification in the interior is not constant, right? If the density doesn't change linearly with depth. If you have changes with density that are not linear with depth, and we know that that's the case because we said the ocean stratification is exponential, so it's clearly that the stratification changes in becoming stronger and stronger towards the top. And this is actually the work of Henri Drey, who just finished his thesis. You get these exchanges between the ocean interior and the boundary, but that's a correction that explains why this flow then can return back to the western boundary. Once they get back to the western boundary above where the flow is southward, the water can return back into the Southern Ocean. Oops, I thought I had another slide that I don't seem to have. So what I'm saying is that this overturning circulation that we generally depict of water coming from the Southern Hemisphere to the Northern Hemisphere and coming back is missing a lot, in the sense that it's taking a zonal average of this picture. So you're always averaging flows along the western boundary, and the flow happens over a mid-Atlantic ridge, both here and there. So all you really see in that picture is the flow coming in and the flow coming out. This is the horizontal component of that circulation. And then you know that there is some diapicnal flow, the vertical component of that flow, that takes the water at the bottom, converts it to the top, and comes back. But it completely misses the fact that there is a big cancellation between water up and down along this boundary. So there is a lot of water mass transformation happening there. So, and I'll try to quickly wrap it up. The question was, as I said yesterday, that there was a lot of skepticism originally on this idea that there should there should be these deep boundary layers with a lot of water upwelling, very thin boundary layers. They tend to be thin because it depends on the thickness of that layer, depends on the scale over which the mixing decays over height, and that's pretty confined to the bottom. And so the question is, why didn't we observe it before? And well, the question is that we didn't sample very close to the bottom, very much deep down, to be sure that we couldn't see effects like this. And so what we proposed was to do an experiment where essentially the idea is that you take a tracer that you can measure. This is a numerical simulation that show what I mean, but the idea was that you release a tracer in one of these rough topography region. And what we want to see, the tracer will be spread by ocean currents, but the idea is that it should slide up. And so this is a simulation over the mid-Atlantic ridge. You should see the tracer is moving up the slope. The mid-Atlantic ridge is becoming shallower in this region. So we just have a channel into the slope. And just to see the tracer supposedly migrating towards lighter and lighter density surfaces. The reason to do the experiment in a canyon is, again, this is a good schematic to illustrate that, is that, as I said, when you have this bottom boundary intensified flow, you also generate flow that are parallel to the slope, and we start to spread the tracer on a very wide region. If you have lateral walls, at least the tracer stays confined. And since it's already difficult to sample a few thousand meters below the surface, you don't want the tracer to go anywhere, otherwise you never sample it again. Something that people have learned by hard experience of losing tracer after you release in deep ocean. So again, what we really want to see is this schematic that I described here. We want to see that if I release a tracer further up in the water column, it should sink, but tracer released very close to the bottom should very quickly rise up along the slope. Can I go another 5 minutes? Or I should really stop? So how do we, the problem is, well, there are logistical problems on injecting the tracer. How do you actually do it? It's not easy. But there is also a problem that once you injected the tracer, how do you convince yourself that you sample it enough and you've actually seen upwelling along a density surface? And so we've done some work to actually find out simple equation that could use simple budget that we can use to actually see how do we estimate directly this upwelling. So this here I'm again writing the buoyancy equation, so the rate of change of buoyancy, the advection of buoyancy, and that should be balanced by this divergence of vertical mixing. The same should be true for any other tracer C, including the one we inject, should satisfy the same equation and experience the same turbulence. If you actually take these two equations and multiply the first one by B and the second one by C, and you average over the whole area where there is tracer, you get a pretty simple budget that tells you the ddt of this B, well, this curly average, or this bracket, is just the average of the tracer phi, that could be buoyancy in our case, multiplied by C divided by C. What I mean is that taking the average, for example, of buoyancy only where there is tracer. So if I look at the rate of change of buoyancy where there is tracer, that is just equal to the average of this divergence of the buoyancy flux that I want to estimate. So this is what I'd like to know, right? Because that is telling me, I keep saying that if this is positive, this is driving upslope flow. So it's a signature that there is upslope flow. But all I need to measure to estimate that is the rate of change of buoyancy of where there is tracer. So if I keep sampling where there is tracer and I look at and I measure the buoyancy of the water there and see how it changes over time, I'm essentially estimating the rate of upwelling. And so if you want a true velocity, you also have to divide by the mean stratification. Otherwise, you have a velocity delta B in time. So it's a velocity buoyancy space. But if you want a velocity depth space, you just divide by that. So as I said yesterday, the first experiment that was done was to measure the sinking of water in the Brazil basin, where a tracer was injected above the mid-Atlantic ridge and let it sink. So this is the picture. The tracer was injected at this point here above the mid-Atlantic ridge and resampled. So the color contours are the resampling after 14 months. And we can apply the formula I've just given you. Now, looking at what was the buoyancy of the tracer after 14 months minus the time, the buoyancy at the time when it was released, divided by 14 months and divided by the stratification. And they found that there was a sinking of about 30 meters per year associated with that buoyancy flux. So indeed, they estimated that there was water coming from the surface down. That's a factor of 10 larger than Walter Monk's estimate or Henry Stommel estimate of upwelling. So it's going in the opposite direction. It's much larger, and we know that it should be larger because all that mixing is confined to topography. So it tends to be much larger there than probably estimated by Walter Munk. But then we went to the Rocaltroph, just off the coast of Ireland last year. And we is the group that I'm working with that group, but I wasn't on the ship. I went to the ship a couple of times, and I decided it wasn't really for me. But I respect people that go to see much more after that. So the Rocaltroph is a nice setup because it's a big bowl, 2,000 meters deep, with very rough topography, very strong mixing, bottom enhanced. There is a deep source of North Atlantic deep water that is formed through convection in the North Atlantic. That's what I was describing at the beginning of the talk. And then it flows all the way south into the Rocaltroph. So we really have a small laboratory experiment in a sense, where you have the dense water coming in, the deep mixing, so we have all the elements we need. And the experiment was done in a canyon on the edge of this trough. And what we did, or at least the part of the experiment I'm describing today, it's work by Bethan, Winnie Katanach, and Matthew Alford primarily. They released dye very close to the ocean bottom, 10 meters above the ocean bottom, in this place where there is a green dot, on a particular temperature surface. They just look at the temperature at which they release it, and then with a fluorometer, with two sets of fluorometers, one using a rapid profiling CTD, so just something you put in the water from the side of the ship, and then also a fluorometer that instead was attached with a mooring at where there is the cross here. And that instead was continually profiling the vertical going up and down. So we have some information about how the tracer was evolving in time. Now you can see that the tracer is injected here. After 4 hours, it started spreading up and down a bit more, not more. It's a non-trivial exercise because there is a very strong tide in the system that is affecting the tracer back and forth. Without that mean tidal advection is not really mixing it, it's just moving it up and down. It's only the part of the tide that breaks that would mix it. So you're going with a ship that can't keep up really with the tide. So you see the movement up and down, and they're trying to sample as much of the tracer as possible. But by just looking at what the tracer is doing, it's very hard to tell whether it's going up slope or down slope in the net, because you see every time there is a flood phase in the tide, it's going up the slope where the whole tracer is moving up, but then the next time it's going down. But instead, what you can do is that you can now plot, well, the tracer in this temperature salinity space, where the black lines are now density values. So this is the equation of state. If I know TNS, I can estimate the density of seawater at a particular depth. So this is where the tracer was, the star is where the tracer was injected. And the circle is where the density at which the tracer was injected, or T temperature and salinity at which the tracer was injected. The star is this average density of the tracer after, for example, 2 hours, 4 hours, and as you keep going. While the color in the background is all the measurements that were made of the tracer, just to give you an idea of the cloud. So you see that the tracer tends to be moving away from the black dot. So the mean density where the tracer sits is getting lighter and progressively lighter over time, over 30 hours, 32 hours, 35 hours. It's moving further and further up. Sometimes it looks like it's coming back down. Something we are looking into most likely is that we are not sampling the whole tracer. So if you miss part of the tracer that was particularly light, all of a sudden you might get effects like this. But in the net, it's clear that the tracer has gotten lighter, and quite rapidly. Over 42 hours, we can see a substantial change of 0.05 kilogram per meter cube, which on such a short time, it was a huge signal that we didn't quite expect even at the beginning. So now we can apply our equation, as I said before, where we can estimate this W by just looking how the tracer is moving in density space. And we get an upwelling rate of order of 100 meters per day, which now is huge. If you remember, we were talking about 30 meters per day of sinking, for example, in the mid-Atlantic region. Now you see that it's a very large velocity, but of course it's confined to a pretty thin layer. So in terms of mass transport, it's probably not very different from what happens above. We know that the two have not completely to cancel, but be of the same order. But you have a boundary layer which is probably an order of magnitude, if not more, thinner than the water above it. So the velocity itself is very fast. So now there is evidence that these large currents along boundary do actually occur, even though they're not easy to sample. Here, there was a whole experiment that was designed just to look very close to the ocean bottom. And so to conclude, I think that bottom intensified mixing drives a pattern of up and down welling along ridges and seamounts. The Brazil Basin experiment documented well this sinking towards the bottom. As we said yesterday, the BLT experiment instead showed quite nicely this very strong upwelling that can happen along the boundary. What I didn't discuss, but what we are publishing on is that now, if you understand this global circulation that is associated with this upwelling and downwelling, you find out that indeed this boundary layer transformation constrain a lot the stratification in the ocean interior and the strength of the overturning circulation. So they're not just passive elements on the side of the domain, but given that all the water mass transformation, meaning the change in density, is confined to this boundary, that's what really sets the stratification, because it's how you can change density in the fluid. They also have important implication for the distribution of the age of water masses. And what I mean is that age of water mass is the time since water supposedly has left the surface. So if you want to know how old the certain waters are, or how long does it take for heat or carbon to get in the deep ocean, now you have very strong inhomogeneities on this water. And when I told you that the overturning time scale is over 1,000 years at the beginning of the talk, well, that's true in a mean sense, but what it's telling you is there is a lot of water that is, I guess we've been kicked out. Have we? It's okay. There is a lot of water sinking very slowly towards the abyss, but then rising very rapidly towards the bottom. So now the age of water masses is going to be quite non-uniform, probably younger waters along boundaries for the part of the water that managed to swell rapidly, and higher ages above it where the water is slowly sinking. There is also a thing that, I mean, since we are not online now, I can say it. Another thing you can bring up is that when you talk about nuclear waste, that would suggest that the worst place to put is in the ocean bottom, because it, oh, okay, I didn't say that. But the ocean bottom might be a very peculiar place. It has also implication for paleoceanography, where we are constrained, and this is something we come up in the last lecture, to collect records that are essentially sitting on the ocean bottom. And to the extent that the ocean bottom is a peculiar part of the ocean where there are these strong upwelling, you have to be pretty mindful in interpreting the data in that context, and not assuming that what happens right along the boundaries represent what happens in the ocean interior, at least in general. Of course, it depends on the specific variable you're looking at.